All right, let's get into Chapter 9, Lesson 2. This is going to be about changing states of matter. In the last section, we learned about the different states of matter and how the particles behave in them. Now we're going to talk about how we get from one state to the other and what each of them are called. So, you may be familiar with the three basic states of matter. We have solids, liquids, and gases. There are, in fact, more. Usually, I have at least one sixth grade student that says, but what about plasma? Yes, plasma is a new, not a new, but a different state of matter. But there's actually way more than that. There are other states of matter that exist, but we don't have to worry about them in sixth grade, solids, liquids, and gases, but just so that you know, there are others, and it's more than just plasma. Take a look at this list. Pretty crazy, right? Anyway, that's for something you don't have to worry about for quite some time, if ever. All right. So this lesson is going to be about changing between the different states of matter. There are two factors that are going to control which state a substance is going to be in. The primary factor or the main factor is thermal energy. There's another factor called pressure, and that can also affect the state of matter. But this section's really just going to be about thermal energy. All right. So we kind of talked about this a little bit in the last section. There is a difference between temperature and thermal energy. Temperature is a measurement, I put that in all caps for a reason, of how hot a substance is. It is an average of how much the particles are moving. In a substance, some particles are moving more, some particles are moving less, and the average of how much they are moving gives us a measurement that we can take called temperature. Thermal energy is different because instead of being an average, it is a total amount of the energy of the motion of particles in a substance. So, temperature is a measurement and it's an average. Thermal energy is a total of the motion of particles. All right. Particles, whenever we use that term, we are referring to atoms and molecules. The more thermal energy there is, the more movement of particles there are in a substance. How much movement and the type of movement that they are doing will determine which state of matter, solid, liquid, or gas, a substance is in. So, more movement comes from more thermal energy, and that will give us changes of state. There are six changes of state that you have to be aware of. Most of them you will hopefully have already heard of before. There are four basic changes of state. The first is melting, and that is when a solid turns to a liquid. If thermal energy in a solid increases enough, it can actually melt the substance. Vaporization is the term that we're going to use for liquid becoming a gas. And again, we are starting off with a liquid. If you increase the thermal energy, you can get the liquid to vaporize and turn into a gas. Condensation is the opposite of vaporization. This is when a gas loses thermal energy and eventually becomes a liquid. Freezing is the opposite of melting. It is when a liquid loses enough thermal energy and will turn into a solid. Now, there are two other cool states of matter that we are going to have to know. These states of matter happen when the liquid phase is skipped entirely. So, sublimation is when a solid will turn directly into a gas. So a solid will skip the liquid phase and go straight to becoming a gas. So if you heat the solid and give it enough thermal energy, that solid will skip the liquid phase and go to the gas, and we call that sublimation. The opposite of that is called deposition, and that is when a gas loses thermal energy, skips the liquid phase, and goes directly to the solid state of matter. Now, I'll give you a couple of examples of those. So, around this time of year, you'll see a lot of spooky fog created by dry ice. Dry ice is frozen, so it's a solid, carbon dioxide. Carbon dioxide, if you lower the temperature, will become a solid. When the block of carbon dioxide gets enough thermal energy, it will skip the liquid phase and go directly to being a gas. Um, and just as a kind of a preview for this week, the fog that you are seeing is not dry ice. The fog that you see is actually water vapor in the air becoming a condensing and becoming a liquid because the thermal energy of the carbon dioxide is so low, it actually cools down water vapor and causes it to condense. So, dry ice, as it goes from solid to a gas, sublimates, and the fog that you see is water vapor, not carbon dioxide or dry ice. Another example of sublimation are air fresheners and unlit candles that you can smell. So these are solids. Okay, the green stuff is a solid, and you never see it become a liquid, but you can smell it. The scent molecules are sublimating and skipping the liquid phase and going straight to becoming a gas, traveling through the air and into your nose where you can smell them. Um, Over time, these solids shrink and you never actually see them melt. They just kind of vaporize. So these solid blocks are sublimating straight into a gas. Candles are the same thing. If you can smell a candle that's not lit, well, it's a solid that is turning into gas particles that travel through the air into your nose and you can smell them. And in this case, it is bonfire nights, whipped pumpkin spice. Mmm, whipped pumpkin spice. Anyway, uh, yeah, it you never see it become a liquid. It's going directly from a solid to a gas, and you smell that gas. The opposite of sublimation is deposition, and that is when a gas goes directly to a solid. And a good example that's coming up around this time of year as well is frost. Water vapor in the air, when the temperature is warm enough, can become dew. And that would be just water vapor condensing into a liquid. But in the winter time, with the thermal energy being as low as it is, the temperature being as low as it is, the water vapor skips the liquid phase and goes directly to the solid phase, ice, and covers everything with frost. All right. So here we have solid, liquid, and gas. And I like this chart because it's showing us that as we increase energy, these ice particles are vibrating. If you remember from the phases of water gizmo, these are just sitting there vibrating in place. They're kind of in formation and they're vibrating. Um, as we add energy, they vibrate more. And if we add energy, they vibrate more. And as we add energy, they vibrate more. And if you keep adding energy, they will vibrate so much that they will break formation and turn into the water phase, the liquid phase. Um, these move around a whole lot more because they've been given more thermal energy. Um, if you keep adding thermal energy to the liquid water, they'll move more and more and faster and faster and faster. And if you keep adding energy, they will eventually break free from each other. They will vaporize, and we get them completely spread apart, and they're moving around much faster. The water vapor are separated from each other, and as they start to lose thermal energy, if we remove thermal energy, they will start to slow down. And eventually, when they come into contact with each other, they'll start sticking together, and we call that condensation. So, water vapor, as it loses thermal energy, will condense back to a liquid. Then, if we keep removing thermal energy from the liquid molecules, um, they will slow down and eventually form a nice formation and then just vibrate in place. We call that freezing, and we now have solid. So, thermal energy, by adding or subtracting, we can get molecules to behave differently and give us our different states of matter. All right. So we're talking about freezing, so we'd better clear up some terminology. Word choice matters, and in science, word choice really matters. So please just stop thinking of the term freezing in just in terms of water. In English, we use the word frozen pretty much just to only really talk about water. For example, when we say it's freezing outside, well, we're talking about the temperature at which liquid becomes solid, water becomes an ice. Okay. So if we say that it's freezing outside, we're talking about water freezing. When we talk about frozen drinks, well, we're talking about ice, which is water that is just in a solid state. When we put food in a freezer, well, we are basically removing thermal energy to the point where water, which makes up a large portion of most of our food, um, to get that to turn to ice, a solid form. So freezing in English just means solid water. In science, the word frozen just means that it's a solid. So if anything that is in a solid state, um, we call that frozen. And that means that your desk is frozen. Your desk is not a liquid. Your desk is not a gas. Your desk is a solid. The metal and plastic are in a solid state. They are frozen. The doorknob on the way in and out of the classroom, it's frozen. It's a solid. We call it frozen. You can even take a hot cooking pot, put it on the stove, and that hot cooking pan could be 400, 500 degrees. But as long as it's a solid, we call it frozen. So a 500-degree um, piece of metal on your stove, we would consider frozen. All right. So as energy is increased, every substance has a unique temperature, and I'm choosing that word carefully, at which point the thermal energy changes the substance from a solid to a liquid. So when we can get, it's not temperature that changes the substance, it's the thermal energy that changes the substance from solid to a liquid. Here are the melting points of some basic kitchen materials. So, olive oil is a liquid at any temperature above 21 degrees. So, if you put olive oil in your freezer, well, your freezer is pretty much set to be 32 or lower. So, olive oil will not turn to a solid in your freezer. So, water will be frozen, but olive oil will not be. Olive oil will be considered melted in your freezer. Butter melts at about 95. Chocolate melts at 97, which is why chocolate will melt in your hand because your body temperature is usually around 98. So you are about 1 degree warmer than the melting point of chocolate. Sugar, you can actually get to melt at 365 degrees Fahrenheit. All right, here's a list of some common substances, and as you can see, we have a wide range of melting points. Bismuth, which is a metal, will melt at 520 degrees. So bismuth is probably not a good material to cook with. Whereas something like chromium has a melting point of 2,939. Iridium would be fantastic. It's 4262 to melt. Cast iron. I have a cast iron uh, skillet. I would have to heat that up to be 2,000 degrees. So, cast iron, as far as a skillet, you can get up to 1,999 degrees and it would be considered frozen. It looks like tungsten down here is the king at 6,098. So you can have tungsten, which is a metal, at 6,000 degrees, and it would be considered frozen because it hasn't melted yet. All right. Uh, the freezing point of a substance is the exact same thing as the melting point, but It's when the thermal energy is decreasing instead of increasing. So as energy is decreased, every substance has a unique temperature, at which point the thermal energy changes the substance from a solid to a liquid. So if I go back here, this says melting point, but these are also the freezing points. So aluminum will melt at 1220, but if it's already liquid aluminum and I decrease thermal energy, when it gets down to 1220, aluminum will freeze at 1220. Our king of the melting freezing points down at the bottom is tungsten. So when tungsten is below 6098 and then I increase the thermal energy, tungsten will melt into a liquid at 6098. Then, if I've got it above that temperature and I decrease the thermal energy in tungsten, tungsten will freeze at 6098. So melting point and freezing point are the same thing. Vaporization and condensation are the just like the freezing and melting point. Each substance has a vaporization or condensation point, at which point it will change states between gas and liquid. If energy is increasing, we call it the vaporization point. If the thermal energy is decreasing, we call it the condensation point. But condensation and vaporization points are the same. All right. Uh, Again, word choice. Vaporization is when a liquid turns to a gas. There are two types of vaporization. There's evaporation and there is boiling. Evaporation is vaporization, but only on the very top of the liquid. Boiling is when the entire liquid is changing states, and a big giveaway is the bubbling. So evaporation and boiling are both just types of vaporization. All right. As I talked about before, there is a second factor that can cause molecules to change states of matter, and that is pressure. So even if thermal energy is constant, and that means not changing, a substance can change state if we force their atoms or molecules into a certain behavior with pressure. We're not going to worry about that in this section. That's for lesson 3. Meanwhile, we're gonna do a Kahoot tomorrow, and it's going to be an activity that's kind of based off of this. So let's take a moment to practice for tomorrow's Kahoot. So here we have a chart of different gases, and here's their melting point, which is also their freezing point, and their boiling and vaporization point. So the question up here is, in what state of matter is ethane at negative 100? So when I go down to the chart, here's ethane, and negative 100 is warmer than the melting point. And that means that ethane will have at least melted. So that means ethane is definitely not a solid. But negative 100 is less than negative 89. And so that means that ethane will not have boiled yet. And that means that ethane is a liquid at negative 100 degrees. So this number, if you look at it kind of like a number line, I would put negative 100 in between negative 183 and negative 89. And if it's in between, then it's in the in between phase, which is a liquid. All right. Our next one is hexane at negative 100. So in this case, if we go down to hexane, negative 100 is lower in temperature than negative 94. Think about negative 100 would be colder, which is a word we're going to have to stop using soon, than negative 94. And that means that hexane at negative 100 will be frozen because it won't have melted yet. And so we call that a solid. All right. Nonane at 100. So here's nonane. Here's the melting point. Here's the freezing point. Is 100 less than negative 54, more than negative 54, but less than 150, or more than 150? Well, 100 is in between these two numbers, and that means that it would be a liquid. All right, butane at 100. I'm going to give you a few seconds. You can pause if you want. When you've got your answer, solid, liquid, or gas, unpause. Meanwhile, I'm going to silently count to myself and let you figure it out. All right, butane 100 is definitely warmer than boiling point, so the substance will have boiled, and that means that butane at 100 is a gas. Next one. Pause if you need to. Zero is warmer than negative 42, and that means that propane at zero would be a gas. Next one. Pause if you need to. All right. Negative 170 is in between these two numbers, and so that means it would be a liquid. Pentane at negative 170. Negative 170 is less than negative 130, and that means that pentane at negative 170 would be a solid, but it would be frozen. 150 is more than 125. It is beyond the boiling point. It would be a gas. 150 is more than negative 30, but less than 174. It's in between, so we choose our in between state of matter, the liquid. All right. So read pages 308 to 315, answer all the questions, and good luck to you this week.